Hey guys, welcome back. Lesson 36. I know that you really like that short lesson from yesterday, so we'll try to keep that going, but I can't promise anything. We are going to still try to get to lesson 40. Hey, that means there's really only about 4 more lessons that we're going to go through, okay? So we're going to keep chugging along. If we get done early, that's great. We are looking at another test, another quiz. We'll do a quiz and then a test. And then we're kind of going to wrap up this year, really. Oh, this is so crazy. So, critical numbers. Let's talk about critical numbers and what in the world are they? The box definition, generally never like. A critical number of a function f is a number c in the domain of f where either f prime of c equals 0 or f prime of c does not exist. So it's saying the derivative is going to equal 0 or it's not going to exist. Okay? In other words, I always like that line below. Critical numbers. Critical numbers will be where a function, the critical numbers of a function, maybe I'll put it, critical numbers of a function is a number. I don't want to go back to that first definition, I'm sorry. Are those values of the domain, which are the x's, right? Of the domain of f, where the derivative equals 0. Or does not exist. Okay, so those are critical numbers of a function. Okay, they give us some great visuals of what that actually looks like. Where in the world can we find something where a derivative was 0? We did that, I don't know, not that long ago, I feel. Maybe a parabola. Down here, if we were to draw the tangent at that bottom point, our derivative would equal 0. Remember, the derivative of horizontal lines are 0. Okay? Where would it not exist? We haven't talked about these too much, other than being vertical. That's always a good option. But if a function, like the absolute value of a function, where it comes down to a point, the absolute value of x, this one is not necessarily straight across, because we could draw it this way, or we could draw it this way, okay? That derivative does not exist. There is no tangent line we can draw and be perfectly sure that that's where it is, okay? So they talk about any time a function comes to a sharp point or has a corner, okay? There could be one, sometimes there are square roots, probably not the best, kind of come angle and then go back like that, kind of like that bird. Yeah? That one, the derivative does not exist. Okay? Sometimes we have functions who come up and they almost go vertical for a while, like that. Okay? This point of tangency here does not exist because it would be vertical. It would be undefined. Okay, that's an x raised to the 1/3 or the cubed root of x. The cubed root of x. That at 0 does not exist. Okay? So those are visuals of critical numbers where the derivative equals 0 or does not exist. Okay? The next page it's talking about local maximums and local minimums. Okay? Minimums are going to be bottoms. Maximums are going to be tops. Okay? So you know maximum and minimum. Local just means we don't have the full array of the graph. Okay? So if we are given some type of graph, regardless of what it looks like, I'll kind of try to do the one in your book. It doesn't matter. if we're going like this and things are coming down and going back up and then turning sharply and going back down and coming up and going down and going this way, it's going that way. We have some pieces on this graph. They give them points. Here we go. Oh, my black line needs to keep going out because I didn't draw it far enough. Okay, at these points, at point A, we have a local maximum. There's a critical number that happens there. It comes to a cusp or a point. There's a critical number at x equals A. There's a critical number at B, where, if we were doing this, my derivative would probably be 0. So they like that being there. At C, it's going to turn again. There's another critical number. Okay? Okay, and then at the bottom here at D, at x equals D, going to have another slope of 0 or a derivative that doesn't exist. And at E, where it makes that turn, where a derivative does not exist. So in this graph, we have labeled 5 critical numbers. Okay, we don't know what's happening elsewhere. And now we're going to look and say, are these critical numbers our local maximums or our local minimums? Okay, we can look and see. If you're looking at a graph, it's pretty obvious which ones are the local maximums and which ones are the local minimums. Okay, if I just were to ask you to ask that question right now, you could all circle the local maximums and the local minimums. Meaning there can be more than one. Okay, local just means around point A. Nothing else is higher on this graph at point A. Or point C, there's nothing around it that is higher than point C or point E. So all these circled in green are local maximums. Okay? They also call them relative maximums. Another word, they will mean the same thing. Okay? Do you see the local minimums? Yes, the local minimums. And I'm pretty sure I misspelled that. Minimums. Or the relative minimums. 2 words, 2 phrases that mean the exact same thing. Relative minimums will mean the same thing as a local minimum, meaning the points around B, nothing else is lower. The points around D, nothing else is lower. Okay? We cannot say it's an absolute local minimum. It's not an absolute minimum or an absolute maximum because we don't know what's going on around it. Okay? So, what's going on beyond the other pieces? We won't know right now. Okay? So now, how can we find these numbers if we're given an actual function? Okay, so we're going to start with that. Find the critical numbers of the function of f. If f of x equals x cubed plus 9 halves x squared plus 6x plus 5. Okay? How in the world are we going to find the critical numbers? And also, where the relative minimums or maximums occur. So not only do we want to find the critical numbers, we need to know what are the local maximums or the local minimums. Okay? 3 questions that we have to answer. Okay, so here we go. We're going to start. So to find these, we'll do that in a minute. The first thing is we have to find the critical numbers. And then we'll decide if they're maximums or minimums, if they're at the top or if they're at the bottom. So what are the critical numbers again? Where f prime is equal to 0. So what should we find first? Yes, we should find what is the derivative of f of x. Okay, you're going to find the derivative first every time. So what's the derivative of this function? X cubed, we have 3x squared. What about 9 halves x squared? Bring in the 2 down, multiply 2 times that. Guess what? Those 2's cancel. That's right, it's just 9x. And then what's the derivative of 6x to the first? Becomes a 6. What about 5x to the 0? Yeah, the derivative of a constant is just 0. Okay, so now we have a function f prime. Okay, and now let's go back to that other part of our critical number definition. It's where the derivative equals what? 0. So we're going to take f of x, f prime, and set it equal to 0. Okay, now we're going to have to remember how to factor. How in the world are we going to factor this? You can plug it into, oh my goodness, quadratic formula. Always it's going to work to give me x equals. I see a 3 I can factor out. So I'm going to go x squared plus 3x plus 2. Is that correct? Yeah, so now I'm pretty sure factors of 2 that add, yeah, to get 3 is x plus 1 and x plus 2. So now, setting this equal to 0, what are my zeros? X equals what? -2 and x equals -1. Those are my critical numbers. I've just solved the first part. Critical numbers. Now the question is, well, are they local maximums or are they local minimums? Okay, so we have x equals -2 and -1. Those are my critical numbers. How are we going to find if they're the local maximum or minimums? We have x's. Could we find the y or the f of x? Yes. So I'm going to go y equals, I'll put a y for the f of x, or we could even put f of -2. That's really what you're trying to find. So I'm going to say -2 raised to the third. It's the original function. Remember that. Plug it into the original function. You're trying to find the y. Plus 9 halves times -2 squared plus 6 times -2 plus 5. That's going to give me a point. You could do this pretty quick in your calculator if you had this function already in there. I don't. So I'm going to do it the long way. Well, I guess I probably should answer one question before I start the next problem. Oh, it's taking off more. Okay, so what's -2 raised to the third? Pretty sure that's -8. 2 squared is 4. 2, that would be plus 18. 6 times -2 is -12 plus 5. I have a calculator somewhere near. That's 10 minus, that's -2 plus 5. Is that 3? Oh my goodness. Is that correct? Yes, my calculator says it. It's my battery is going to die. We'll plug it in just a minute. So now we have 1 point. So I'm going to go over here and put one of my points. X is -2, Y is 3. That's one of my critical points. Okay, that's where something happens. Thank you. I'm going to close you. And then I'm going to go ahead and go to the other one that I need to know. So I'm plugging in -1. So I'm plugging in my calculator, in my computer too, sorry. So y equals, or f of -1 equals, -1 cubed plus 9 halves times -1 squared plus 6 times -1 plus 5. All right, this might be a fraction. It's okay. -1 cubed is still -1. -1 squared is a +1. So it's plus 9 halves, which we all know is 4 1/2. It's okay. Minus 6 plus 5. All right, so I'm taking, this becomes -1. I have -1, -2 plus 4 1/2. So that's 2 1/2, right? I think so. I'm going to look back at my book. Yes! Look at there. I have 2 points. So I have another point that's -1. a positive 2.5. Why did I use a comma? 2.5. Okay, so now looking at that, I might need to kind of sketch a graph to see what type of function is this. It was a cubic function. What do we know about cubic functions? They're coming, I'm going to do this and then erase. It's coming up and down and up. So ultimately, critical numbers are going to be these, where our derivatives are going to equal 0. And I probably put a lot too many dots on there. Okay? But we have some things that we know, right? There are a few things that we know. If I was scrolled up to the top, I would see there was a plus 5 on the end, right? If x equals 0, we're at 5. We know it's coming up from the bottom. We know it's going to, at negative 2, it's going to be at 3. So there's that first point. At negative 1, it's going to be at 2.5. So it's going to be below. Probably not the best. It's not very far below it, because this is at 3. Really not good in drawing to scale. I know. Imagine that, what happens when nobody's here with me to help me do these things. Okay? So let me draw a little bit different. So here is a positive 2.5. Here's a positive 3. Here's a positive 5. We know it has to go through all 3 of these points. We know it also positive cubic function is coming from down low up to down to up. Okay, that's a sketch of the graph. We've given enough points. We have 2 critical points here and here. Now, once we see this, we can see which one is the maximum. Yeah, that one where the y value is higher is the local maximum. Here where the y value is lower, it's the local minimum. Okay? Have we answered all our questions? Yes, we have. I'm going to try to keep this short and make another video for the rest of this, which there's really not that much more. And then we'll be done. See you guys later. You guys are awesome. Bye.